Okay, so hello everyone. My topic is on the origin of red spirals. Does assembly bias play a role? We first come to the introduction section. Now, what are these red sequence galaxies? The distribution of optical color of galaxies shows bimodal character with two distinct peaks. The peak corresponding to higher optical color represents red sequence, whereas the peak corresponding to lower optical color represents blue cloud. And studies have found that the dip in between the two peaks occurs at around 2.2. Now, the blue cloud galaxies are actively star-forming galaxies, and most of them are having spiral morphology, whereas the red sequence galaxies shows low star formation rate, and most of them are having elliptical morphology. However, studies with galaxy zoo data reveal that 20% of the galaxies in the red sequence have spiral morphology. The Galaxy Zoo data gives visual morphological classification of nearly 1 million galaxies by citizen scientists, and the data is available in Sloan Digital Sky Survey data release 16. Now, what are the factors which affect star formation rate in red spiral galaxies? Now, studies have found that the red galaxies mainly reside in high density regions, which are one-dimensional filaments of the cosmic wave, and thus environment can play a role in quenching their star formation rate. The other factors include tidal interactions, minor mergers in which two low-mass galaxies merge together to form a higher-mass galaxy, galaxy harassment and strangulation. Mass quenching can also play a crucial role as the red galaxies are massive galaxies, and studies with the hydrodynamic simulation has found that there exists a critical stellar mass which is 3 into 10 power 10 solar mass, which corresponds to a critical halo mass of 10 power 12 solar mass, and galaxies having stellar masses greater than this critical value mainly suppress their star formation rate through mass-driven quenching. The presence of bar in spiral galaxies can also affect their star formation rate, as the bar-induced torque can transfer gas from the outskirts to the center of a galaxy, leading to formation of a bulge. The bulge developed actually creates a deeper potential well, which can stabilize the disk against collapse. The spiral galaxies can also fall into the red sequence category due to the internal reddening in color caused due to dust. Now, studies with n-body simulation has found that the mass and angular momentum of dark matter halos are sensitive to the large-scale geometric environment, and also the clustering of these dark matter halos depends on the halo formation time at fixed halo mass, which is known as assembly bias. And thus, in related to this, the galaxies present within the dark matter halos with fixed stellar masses can also have different assembly histories, which is known as galaxy assembly bias, and thus different assembly histories of galaxies can affect their different physical properties as well. And the assembly histories of galaxies and their large-scale geometric environment are correlated, and if a property is found to be sensitive to its large-scale geometric environment, implies the effect of assembly history of that galaxy on that property also. Now, in this work, we try to determine if assembly histories of spiral galaxies are responsible for determining their optical color, and we do this by measuring the mutual information between large-scale geometric environment and optical color of spiral galaxies. Now we come to the data section. Here in this work, we use the 16th data release of Sloan Digital Sky Survey to download various spectroscopic and photometric information of galaxies. While downloading the information, we consider only those galaxies for which the Petrosian magnitude in the R band is less than 17.77, and which are spatially located within a right ascension of 135 degree to 225 degree and declination between 0 degree and 60 degree. We identify morphology of the galaxies from Galaxy Zoo and classify them as elliptical, spiral, and uncertain based on the devised vote fraction for each property given by citizen scientists. We also download the information of 4000 angstrom break strength D4000 from MPA JHU spectroscopic catalog. Now, further to remove any luminosity bias in our sample, we volume limit our sample by restricting the absolute magnitude in the R band to -21, and use of this absolute magnitude cut restricts the redshift of the galaxies to 0.12. Now, here in this work, we determine the mutual information between large scale environment and color of spirals. And To do this, we extract the largest cubic region that can fit within our volume limited sample of size 181 H inverse megaparsec, and also to determine if any correlation exists between large scale environment and color of spirals at fixed stellar masses. We constrain the stellar mass of all the red and blue spirals present in the extracted cube within 2 into 10 power 10 solar mass to 2 into 10 power 11 solar mass. Now, here in this work, we classify all the galaxies in our sample into red, blue, and green using fuzzy set theory. We define the fuzzy set corresponding to redness of the galaxies as given in equation 1, where U minus R color represents the fuzzy element and the corresponding red membership function is mu R is given by equation 2. We choose here a sigmoidal membership function based on the fact that the distribution of color of galaxies shows bimodal character. Also, the value of constant A is chosen in such a way that the galaxy with the highest optical color should have mu r equal to 1 and galaxy with lowest optical color should have mu r equal to 0. The value of constant C is chosen based on the fact that the dip in between the two peaks in the distribution of in the color distribution of galaxies occurs at around 2.2. Similarly, we define the fuzzy set corresponding to blueness of the galaxies by taking the fuzzy complement of redness, and the corresponding blue membership function mu b is given in equation 3. The, the fuzzy set corresponding to greenness of galaxies is obtained by taking the fuzzy intersection between redness and blueness, and the corresponding green membership function is shown in equation 4. The factor 2 in front is multiplied in order to ensure that the galaxy with optical color equal to 2.2 should be maximally green with mu g equal to 1. This plot shows the variation of three membership function as a function of color, and in our sample we identify red galaxies as those for which red membership function dominates the blue and the green membership function. Similarly, the blue and the green galaxies in our sample are also identified in a similar manner. The more details of this classification scheme is present in this paper as shown here. Now, we obtain the mutual information between color and environment of spirals to determine if any correlation exists between these properties, and in order to do this, we extract the largest cubic region that can fit within our volume limited sample and consider only the red and blue spirals present within the cube. We further subdivide the cube into smaller subcubes, and the information entropy associated with environment at scale D is given by the form of Hx, where D represents the side of the subcube and Pxi gives the probability of finding a spiral galaxy in the ith voxel. The simplified form of Hx is also shown, where capital N represents the total number of red and blue spirals considered in the cubic region, and Ni represents the number of galaxies in the ith cubic voxel. Similarly, the information entropy associated with color is given by the form of Hy, where Nb and Nr represents the number of blue and red spirals present in the extracted cubic region. The mutual information between environment X and the color Y is given by the form of Ixy, where Hx represents the information entropy associated to environment only, and Hy represents the information entropy associated to color. The joint entropy between environment and color of spirals is given by the form of Hxy, in which Pxi, Yj gives the probability of finding a particle in the ith voxel having jth color. In our analysis, we consider two colors. We consider only the red and blue spirals. The simplified form of the joint entropy Hxy is also shown here. Now we come to the result part. Now we compare the distributions of stellar mass, star formation rate D4000, and local density of all the red and blue spirals present in our volume limited sample. The local density of each spiral galaxy is calculated by taking the distance to its fifth nearest neighbor. We find that the distributions of the different properties corresponding to red and blue spiral are statistically different at 99% confidence level. We test this difference by doing a Kolmogorov-Smirnov test, and in order from the distribution of the local density of red and blue spirals, we find that the red spirals mainly reside in high density regions, whereas the blue spirals mainly reside in low density regions. And in order to ensure that if the differences in the properties are due to the local environment associated with red and blue spirals, we further divide our red and blue spirals in our volume limited sample into low density and high density regions based on the median density of the combined red and blue spirals present in our volume limited sample. Now, in both the low density and high density regions, we again compared the distributions of stellar mass star formation rate and T4000 and found that the two distributions corresponding to two populations vary statistically at 99% confidence level. The plot here shows the distribution of stellar mass star formation rate and D4000 corresponding to red and blue spirals residing in low density regions. The plots here shows the distributions of the same properties corresponding to red and blue spirals residing in high density regions. From this, we infer that the differences that the differences in the distributions of the observed properties are not occurring due to the local environment associated with red spiral and blue spiral only, and assembly history of the spiral galaxies are also responsible for creating these differences. Now, we calculate the mutual information between large-scale environment and color of spirals. The plots here shows the mutual information as a function of length of the subcube. The red curve in the two plots shows the mutual information of the original spiral distribution in the cubic region. From this curve, we find that the mutual information decreases with increase of length scales and is non-zero even at the largest length scale, which implies that there exists a correlation between a large-scale environment and color of all the spirals of all the red and blue spirals considered in the cubic region. Similarly, by keeping the spatial distribution of the spirals in the cubic region intact, we randomly tag the spirals as red and blue in such a way that the total number of red and blue spirals present must be same as that of the original distribution. And we then again calculate the mutual information as a function of length of the subcubes and find that the mutual information decreases with increase of length scales and approaches zero for larger length scale. The result is shown in yellow curve in the left panel. Similarly, we create a mock Poisson sample and again randomly tag the spirals as that explained previously, and we find that the mutual information corresponding to the Poisson sample and the sample in which the spirals are randomly tagged while keeping its spatial distribution same follows nearly similar behavior. Now the plot in the right hand panel shows the mutual information in which the cubic voxels are first randomly shuffled within themselves and then followed by a random rotation. In this way, due to this procedure, due to this random shuffling followed by random rotation, destroys any destroys any special pattern of the core structures which are present larger than the length of the subcube. Random shuffling the voxels followed by random rotation doesn't change the information entropy associated to environment as the number of spirals in each cubic voxel remains unchanged, and also the information entropy associated to color will remain unchanged as the total number of red and blue spirals present in the new distribution is same as that of the original distribution. We find that the mutual information in of the distribution in which the voxels are shuffled followed by random rotation decreases with increase of length scales and approaches zero for larger length scales. Now we come to the conclusion section. First, we compare the distributions of stellar mass star formation rate T4000 and local density of red and blue spirals and find that they are statistically different at 99% confidence level. And in order to ensure that if the differences in the properties are occurring due to the local environment associated with red and blue spirals, we further subdivide the spirals into low density and high density regions based on the median density cut. We again compare the distributions of stellar mass star formation rate and D4000 of all the red and blue spirals present in high density and low density regions. And there also we find that the differences in the distributions of observed properties are statistically different at 99% confidence level. From this, we infer that the differences in the distribution are not occurring due to the local environment associated with red and blue spirals, and assembly history of the spirals also plays a role in creating these differences. We further test if the color of the spirals are sensitive to the large-scale geometric environment by measuring the mutual information between them at fixed stellar masses. We get non-zero mutual information for our original spiral distribution in the cubic region, and also the differences between the original distribution and the distribution in which the color of the spirals are randomly tagged, and the differences between the original and the distribution in which the cubic boxes are randomly shuffled followed by random rotation is statistically significant at 99% confidence level. From our analysis, we conclude that the correlation between color of spiral galaxies and their large-scale environment are statistically significant, and thus color of spirals exhibit an additional dependence on their large-scale clustering due to assembly bias. The hydrodynamic simulations have shown that assembly bias may lead to wide variation of cold gas content within the halos. The halos formed earlier can contain more amount of cold gas than the halos which are formed later, and thus they are more vulnerable to quenching. And as a whole, we conclude that origin of red spirals have a combined role of local environment and assembly bias as well. The archive link to this paper is shown here. So that's all. Thank you.